Hello. Okay. So, hello everyone. I'm Téo, and I'm a researcher at LMU. I'm a postdoc, and today I had the chance to do this talk in a movie theater. I'm really happy to be here, and I will talk about AI again. I'm really sorry. I know you're like completely fed up about AI, saturated, but we're gonna talk about it again. So I'm really sorry, and we'll talk about the theories, the people, and the technology behind AI. It's not my research, it's actually other people's research, and from the 40s to now, because it's things I have been reading during my PhD. I was curious about what do we call AI, what do we call human-computer interactions, those kind of terminologies and research. And so I have been reading stuff, I was really into it, and I hope that I can transmit these readings and stuff I have been reading for a couple of years. Yeah, so is it working? Okay, so as an example, no longer than a few weeks ago, I read this article about AI pioneers claiming that human-level intelligence is already here. And so, of course, this is very frightening. Who are those people? What do they agree? What do they really agree on something? And so these kind of questions, I hope that this talk will help to contextualize in a longer period of time. And so we'll get back to this article later. So as I mentioned, we'll start from the 40s to now and cover 3 periods of time that I called with Star Wars movie names. So the first one is a neural hope. And this period is dominated by a paradigm called connectionist AI. So we'll get later to what it means, connectionist approach of AI. Then there is a second period, the symbolic menace. So it's another period where researchers had different views on what is AI, and this is called the symbolic approach. And finally, there is a revenge of the connectionist back on the symbolic researcher, and this is a revenge of the neurons. And in every period, I will show you some archives from the time, so you can get a sense of the spirit of how people were talking about AI, what they were doing, and I hope these videos can help you to understand what was going on. And this work, this lecture is really inspired from 3 researchers and articles that I list here. So if you want to dive deeper into those stuff, please have a look to those lectures. Oh, okay, of course. Okay, so let's start in 1943 with one researcher called Warren McCulloch. So this researcher, as you can see, this was a TV interview, a professor which is very confident. He was described as a wild bird, chain-smoking neuropsychologist slash philosopher slash poet who lived on whiskey and ice cream and never went to bed before 4 a.m. So he formed an unconventional duo with another researcher, much younger, 25 years younger, very shy. He was struggling to find a place to live and working little jobs. And they met at the university, and together they tried to answer one question, which is, can the biological nervous system be considered a universal computing device? So on this image, you see neurons that connect to each other. And they were trying to think, can we model those neurons? And can we compute with neurons? So this is a neuron. There is the cell with the axon, and they connect to each other, right? And they send electrochemical signals to each other. So one neuron receives inputs from other neurons and send input to other neurons. So it's a network. And they decided to model this neuron with a function, a mathematical function that takes inputs, so-called x1, x2, and send an output. So this is the only math of the lecture, I promise. What it says, if the sum of x1 and x2 is greater than a threshold called theta, then you have an input. Otherwise, there is no input. So what it means, if you fix this weight, this parameter to 1, what does it mean? If X1 fires, and it means that the sum of X1 and X2, 1 plus 0, is greater than this parameter, so the neuron fires an output. If you change this weight, and you choose 2, then you need both to be on so that there is an output. And so they thought that this is actual logical gates. It's a logical function called AND or OR. And so you can combine those neurons to compute things like you do with logical functions. So I'm not going to enter more into details, but one question they didn't answer is how those weights can be self-adjusted. And if you think about a network, it means how can this neural network learn from experience? And so they didn't really answer these questions. But later, another researcher called Frank Rosenblatt actually worked on this. This is a screenshot from his notebook, and you can see those networks of neurons from a mosaic of sensory points. So I guess what could be your eye cells, to some connected layers of connections, and this layer is actually the output. And he thought that maybe if you get an output and compute an error based on an expected output, you could have some feedback circuits to change the weight of this network automatically. And it didn't only theorize this neural network theory, but also try to build a machine that could do that. And so that's what you see here. This is a mosaic of sensory input. It's actually a sensor, a camera. And those spaghetti cables, it's actually all the connections between the different neurons. Okay, so let's have a look to the machine he and his team built. It's called the Mark I perceptron. And it's the first computer that could learn new visual categories by trial and error. So you try something, is it correct? No, then you adjust the weights and you try again. And here you see Frank Rosenblatt connecting neurons. I'm not super sure what he's doing in this spaghetti of cables, but probably connecting neurons together. Here you can again see Frank Rosenblatt with a stimuli. So this is the input, the letter C. This is probably the camera with a lens, and probably here there is a sensor. And you can see that it's checking on a very old school screen that the letter C is actually into the machine, and probably the rest of the machine in all the neurons to compute the output. And now I will show you a video, an archive video from that time, showing a researcher talking about the perceptron.
Scientists built a few working perceptrons, as these artificial brains were called.
He's using it to explore the mysterious problem of how the brain learns.
This perceptron is being trained to recognize the difference between males and females. It is something that all of us can do easily, but few of us can explain how. To get a computer to do this would involve working out many complex rules about faces and writing a computer program. But this perceptron was simply given lots and lots of examples, including some with unusual hairstyles.
But when it comes to a beetle, the computer looks at facial features and hair outline and takes longer to learn what it's told by Dr. Taylor.
Okay, so that's the perceptron in action. So was it hyped? Was it hyped like today? Well, in the New York Times, page 9, so not the front page, on the very bottom here, there is an article interviewing Frank Rosenblatt. And Frank Rosenblatt actually said, only one more step of development, a difficult one, okay, but only one is needed for the device to hear speech in one language and instantly translate it to speech or writing in another language. So just one little step, and we're here. And of course, in the US Army, the Cold War, they were really interested in translation. So, okay, let's fund this research. And so who was paying the Rosenblatt research is mainly the US Army. So that's for the first part from the 40s to the mid 60s, and that's the connectionist paradigm of AI. What does it mean? It's a belief that intelligence can emerge from the interaction of simple units, the biological neurons. And if you simulate, if you build those neurons, you could potentially reach machine intelligence. But then came another period of time dominated by the symbolic approach of AI. And one researcher called Marvin Minsky, he was a bit critical of Frank Rosenblatt, and he said, you know, perceptron is great, Frank, truly, I'm a big fan, but it might be completely useless for actual intelligence. I mean, it cannot even model the XOR function. You all know what a XOR function is. So I love the idea, but it will look great in a museum one day. So this quote is made up, obviously, but it's basically what he wrote in this book called Perceptron, and that was a critique of Frank Rosenblatt's lifetime research. So it was really harsh, and it transfers the funding from the connectionists to the symbolic researchers. And on top of that, Frank Rosenblatt died a few years later in a boat accident on a lake. So this was really the end of the connectionist period of AI, unfortunately. So what is a symbolic approach now? It's a belief that intelligence employs symbols to represent problems, but also the logic to solve those problems. What does it mean? So this is a picture of all the symbolic AI researchers at a conference, a very famous one. Why? Because it's at this conference that they decided on the term artificial intelligence as a research field for their research. And it's still the term we use today to describe all this technology, all this research, all this industry now. So the term really appeared at on this day at the Dartmouth conference in 1956. And you can see Marvin Minsky and other very famous researchers along his side. Okay, and why do they have this approach that we need symbols? Because the 50s, it's also the apparition of programming language. And you can see the power, like this dissociation between hardware and software. And it's no wonder that those researchers might think, okay, we need to program intelligence into the machine because programming is so powerful. It's also the revival of linguistics with Noam Chomsky, and maybe this overconfidence into rationality, that rationality is above other types of cognition. And as a consequence, those researchers, they loved chess. They loved rational games where they could experiment with artificial intelligence. And if the computer can beat a human in chess, that means that this computer should be super intelligent for sure. And so, yeah, you can see researchers playing chess or checkers against computer. Another task they love is theorem proving, because there is no uncertainty. It's about deriving facts from rules. So that was a symbolic approach of AI. And who was paying them? Again, some other bodies of the US Army. Because they thought, okay, this is a way to beat the Russians. And so, yeah, they were funding the research. Was it hyped? Yes. Even maybe more than the connectionist period. And Marvin Minsky, for instance, in Life magazine, he said, in from 3 to 8 years, we will have a machine with the general intelligence of an average human being. I mean, a machine that will be able to read Shakespeare, to grease a car, to play office politics, to tell a joke, and to have a fight. At that point, the machine will begin to educate itself with fantastic speed. In a few months, it will be a genius level, and a few months after, its power will be incalculable. So that was 1970, sorry. So it was really hype, but at some point, the US Army was like, okay, so where is the Russian translator you promised? And Marvin Minsky was like, yeah, we're working on it. Just a few more years and we get there. And that was the first AI winter. So funding cuts, some really harsh reports against the symbolic approach of AI. And yeah, so a lot of frustration on the research public funders. Okay, so this was the first winter of AI. So if we recap from here, I know it's a lot of information, but we had the first neuron model, the first perceptron capable of learning by trials and error. And then we have another paradigm, the symbolic AI, and they loved chess. Okay, maybe, is there some question? I don't know, maybe it's time to pause a bit and think about, or should I move on? Okay, let's move on. Yeah, oh, sorry. It's a good question. I think it should be, my opinion, I wasn't born, but it should be both, I guess. Probably some sensible stuff, very application-wise, maybe was, but I know that if you look on the Google Scholar page of those researchers, you can sort by years, and you can see that during those years, they have publications, so they produce research like any researcher do. So I think it probably was a mixture of both. But as I mentioned, they were so far from actual application. I think, yeah, it was too abstract, and so they were publishing it, I would say. So that's my intuition. Yeah. So, yeah.
Do you think there is a kind of competition between the development of computers like calculating machines, which I think have made very much success during the 60s, for example, calculating or supporting programs like the NASA program?
So I think one change in the 50s is this shift from mainframe computers, so the big computers that occupy a full room, and that's maybe what you described, NASA computing, calculation. I think at that, so they also needed those big computers. If you see the pictures, you see rooms with giant computers, and so it was a lot of investment to do this research. I'm not sure if it was competing for resource, but I read a researcher saying that once the winter of AI arrived, those machines were a bit useless. So there were new research going on, and that actually what I'm transition to what I'm going to talk about. It's more about this human-computer interaction. And so this is this period of time in the late 60s where it was a bit like, okay, let's try something else with machines. And the idea of human augmentation, so from a researcher called Doug Eigenbart, sorry for my pronunciation. So the idea was to leverage computing to augment human intellect. So not building intelligent machines, but using machines to help humans performing tasks. And the researcher behind it was called Douglas Engelbart. And why I think this occurred at this time is because the late 60s in the US and in the Silicon Valley, it's also the counterculture of hippie movement and the empowerment of individuals and communities. So in this technological bubble, there is also hippies in the labs, very interested in the technology because they are not against the technology, but also the techno science. And 1 year after the Summer of Love in '68, this researcher is presenting something called the mother of all demo. Why it's called like this? Because he's demonstrating a computer and all the features we know now for our personal computers, which includes a graphical user interface with Windows and a file system, hypertext links, 2 computers connected at a distance for the first time. So this was like the premise of internet. Video conferencing, so Skype, Zoom, I mean, back in the days. and cooperative file editing. So like in Google Docs, you know, you can see the pointer of the other person. And of course, the computer mouse. So this was like, wow. So here is the mother of all demos. Why it's called like this? Because it set the standard for those tech keynotes that, of course, Steve Jobs with the little microphones doing a live demo. So I think this set the standard for this kind of exercise.
The research program that I'm going to describe to you is quickly characterizable by saying, if in your office you as an intellectual worker were supplied with a computer display backed up by a computer that was alive for you all day and was instantly responsive to every action you had, how much value could you derive from that? We're going to try our best to show you rather than tell you about this program. And in a second we'll see the screen that he's working and the way the tracking spot moves in conjunction with movements of that mouse. I don't know why we call it a mouse. Sometimes I apologize. It started that way and we never did change it. Can you hear me, Don? Let's turn it over and we'll see right. Its principle is that there are two wheels that roll on the surface. But since they're at right angles and kind of sharp edges, one will roll and the other slide in one direction. So I could get myself some material on my blank piece of paper, and then I'd say, well, this is going to be more important than it looks. So I'd like to set up a file. So I tell the machine, all right, output to a file. And it says, oh, I need a name. I'll give it a name. I'll say it's sample file. And I'll say, please output it. It says it did. And then it comes back automatically with an origin statement or header telling me the name of the file and the date and the time and who established it. Yeah. I'd like to see you while I'm working on it. So before I can do that, I have to set up my display in a certain way. Now, computer, do the automatic switching that'll bring in a camera picture from the camera mounted on his console, such as the camera mounted on mine is. Hi, Bill. That's great. Now we're connected audio. You can see my work. You can point at it, and I can see your face, and we can talk. So let's do some collaborating. You're silent. Oh.
What do you want me to say?
Yeah. There's nobody here but a large audience, Bill.
All right.
All right.
Okay, so that was Doug Engelbart and his team working on human augmentation. And I think it's a sort of orthogonal direction to the goal of building intelligent machines, because the orange and blue part, this was a debate, how to build intelligent machines. But this human-computer interaction was a sort of a tangent to this idea that machines should augment us. And I think it also inspired some later AI research, for instance, the expert system in the late 80s and 90s. And this idea, so this is a researcher behind it, and this idea is like you can, those AI systems can encapsulate knowledge from experts, for instance, a medical doctor. So this doctor will enter in the machine the symptoms and the rules to deduce all the symptoms or the disease from those symptoms. And so you have this set of facts and rules, and you have an inference engine that can deduce new facts from those rules. And of course, a user interface for someone that is non-expert to actually ask the machine about new symptoms and get a response. And so this idea of embedding expert knowledge into the AI system for users to query about. So this was expert systems. The problem, so it got some application in chemistry and medicine, but there was a problem, this technological dependence on a certain type of machines called the Lisp machine that could run the programming language called Lisp. This machine looks like this. It's like the size of a fridge. You have a screen, and you have to enter the rules and the facts to build an expert system. So here is another video, a TV show that I think summarizes all this period of the symbolic AI, from their passion to chess to the expert systems.
Welcome to the Computer Chronicles. I'm Stuart Chaffee, sitting in for Gary Kildall this week as Herb Lechner of SRI. Herb, we think of chess as the ultimate game of skill, a game that requires mental agility, intelligence, if you will. Yet here I am playing a game of chess with a computer, which is analyzing board positions and applying a certain kind of intelligence to figure out what its next move should be. That's the subject of our program today, artificial intelligence. And in some people's minds, AI suggests attempting to duplicate the way a human brain works. Is that what AI is, in fact?
Not in most modern AI research, Stuart. Early research in AI looked at duplicating human thought processes, but current AI research is more concerned with duplicating the end result of intelligence. And computers that act as experts in expert systems, and computers that can communicate with us in our language, understanding some of the context of that language, are two areas that are receiving a lot of attention in artificial intelligence research today.
A current application of inferential knowledge engineering is in the field of expert systems. Programs like this Oil Exploration Advisor. Developed to assist drilling rigs in remote areas, the program behaves much like a qualified specialist. It asks questions of its user and then gives advice on how to avoid or correct accidents so common in drilling operations. If at some point in the line of questioning the user becomes confused by the query, he can ask the program to explain itself, simply by entering why. The advisor responds with a specific source behind the question and explains its reasoning up to that point. The symbolic processing behind the human-like talents of this program have found applications in a broad range of fields, from medicine to robotics. Joining us now is Tom Kaler. Tom is Director of Applied Artificial Intelligence at IntelliGenetics. Tom, you've got a complex system here. First of all, tell me how this would be different from the system we saw in the first part of the program. Okay, Tom, this system runs in Lisp. Why is Lisp the right language for an AI application?
Well, one of the reasons that Lisp is so important is that you need to have very powerful symbol manipulating capabilities. Decision making is primarily a symbolic activity. Knowledge representation is primarily symbolic, and you need that kind of capability.
Okay, thank you. Herb.
Okay, so you have everything here. You have the chess, you have the ancestor of ChatGPT asking why, and you have the expert systems, and the Lisp. The Lisp language is very important for AI. The problem is there was a collapse of the Lisp machine market because of this personal computing. So those bricoleurs, like DIY scenes that build personal computer cheaper, and they get more powerful. And so in the end, the benefit of the Lisp, this fridge size computer, was really too little. And so there was a collapse. And with it, a bit of the research on symbolic AI was a bit impacted. And so this is one of the causes of the second winter of AI, and probably the end of this symbolic period. And of course, at the same time, there was a boom of this human-computer interaction idea that machines should augment us, individuals. And so it was a boom of personal computing, not only in the workplace, but now in everyone's house, and also internet, of course. And HCI also developed as a field, because you remember AI, artificial intelligence, was defined to describe this research field. But there is also a field called HCI that try to understand people and technology together, but also try to design new interaction technique, whether on screen or this kind of virtual reality. And of course, now we have computers in our pockets. So also this idea of ubiquitous and mobile computing. And this field is at the crossroad of design, engineering, and psychology, because they try to design interactions, but also understand how people interact. And those conferences are really interesting if you go nowadays, because you have so many ideas, and for instance, you have speculative design, like this device from this researcher, which actually is a robotic finger on your mobile phone to get more affective interaction with your device. You have also critical and intersectional HCI, trying to see the interaction of human and computer under the prism of identity and gender, race and class. You also have a strong connection with the arts. For instance, with this researcher slash artist, Atao Tanaka, which is performing, controlling sound synthesizer with muscle contractions. So all those crazy stuff, including also very technical stuff, can be found in those HCI conferences. And I think that's a great place to attend. And it's a really experimental and interesting research field. Okay, so let's back to AI, because HCI is a sort of a tangent, right? So let's back to AI and the goal of building intelligent machines. So we saw that there are two winters, here and here, and now this is our present time from the 2000 to now, and it's a revenge of the neurons. The neuron spikes back. But before that, there were some scientific locks to the success of the perceptron and the neural network. One of them was backpropagation. I know it sounds difficult, but how to optimize a neural network from the error it makes, but across several layers of neurons. So this idea that you have an error and you propagate across different layers of neurons. And this was solved by two researchers called David Rumelart and Geoffrey Hinton. And so now you have these layers and you try to classify cats and dogs, for instance. And based on the error, you can tune every layer of your neural network from the beginning, from the end to the beginning. So this was a scientific achievement. There was also technological locks. One was the availability of data. And this was, of course, solved by the boom of internet. Now people can contribute to data sets for those machines to learn. And one researcher called Fei Li really worked on this, collecting data for the researchers to train machines. And one of them is ImageNet, which is a collection of images with labels. So every image is annotated. The last one is parallel computing, because those neural networks, they are really expensive to run and to train. So you need specialized hardware called graphical processing units, so you can parallelize every calculation. And this was solved by mainly one company called NVIDIA, and his CEO, Jensen Huang, who developed those graphical processing units mostly for video games and all the graphics. So those limitations, all those locks were gone, and now you can train a neural network. Maybe I skip this part because it's basically the process of training a neural network. You have an image. The image is composed of pixels, but you also have a label. This is a dog. So those pixels, you can form a very long table, and every point, every pixel has values, okay? And if you feed it into the network, you get a response. It's 95% sure it's a cat, but we know it was a dog, right? We saw it. So what you do is you compute an estimation of the error called the loss function. You do the backpropagation to tweak all these little parameters in the neurons. Okay, so we change everything. And you repeat that on your huge database because you have those labeled data from ImageNet. And you use, of course, your graphic GPU, your graphic card. And with all of this, you can achieve this supervised learning. So Yann Lequin was one of the first to apply this supervised learning to a concrete application. The recognition of handwritten digits. So, you know, if you read a letter, it's very hard sometimes to read people writing. So why not using a machine and this paradigm to read those numbers? So this is a video of him showcasing the early prototype of hand digit recognition. So he has a camera, and he feeds some handwritten paper into it, and the machine, thanks to neural networks, can recognize all the digits almost instantly. And even some weird, some really fancy numbers, the machine can succeed, yeah. So this was in Bell Labs in the US. And you can see his colleagues. This is probably the person who solves the backpropagation, first author on the paper. Okay, so this was one of the first applications who got actual commercial application in the post office industry, or I'm sure it's an industry. Was it hyped? Not at all. At that time, this is a quote from a paper, who interviewed some researchers, and one researcher was saying, at the time, if you said you were making a neural network, you couldn't publish a paper. It was like that up until 2010. It has been filled. I remember one time, Yann Lequin was at our lab as a guest professor, and we had to make the effort of eating with him. Nobody wanted to go. It was bad luck, I swear. He could cry. His publications were refused at the CVPR. His methods were not trendy. It wasn't sexy. So, yeah. So doing neural networks, bad idea at the time. Until this event, a conference in 2012. So this is an actual picture of this conference called ECCV, European Conference on Computer Vision. And what they do at this conference, they organize a competition with ImageNet, this database of images. And they say, okay, you can form teams and you compete, and the teams that have the best accuracy win the competition. And one team was composed of Geoffrey Hinton, Ilya Sutskever, and Alex Kripkevsky. They won the competition with a neural network. Not only they won, but they won by 10% accuracy, which is huge progress compared to the second position. So almost 10% increase of performance. So this was huge, so huge that it's almost instantly changed people's perception about neural networks. And this is what we call the era of deep learning, because you have those large neural networks and you have to train them from large quantity of data. And this deep learning approach conquered all related research fields across image processing, sound or speech processing, natural language, protein folding. All those fields now, they use deep learning. And before, it was different communities, different technology. Yes, and so although it's based on neural networks, the architecture of how to compose those networks, those neurons together really changed. And there is a lot of creativity from researchers to invent new architectures to combine neurons together. So here it's examples of different types of neural networks, and they all have different architectures. And one something to keep in mind is that deep learning is very hardware heavy. You see Geoffrey Hinton with a pile of GPU, and you need, again, it's a bit back to the mainframe approach. You need a room with those GPUs to do the computation. And this video shows from the 2000s to now all the technologies that are based on deep neural networks. So face detection, those kind of segmentation tasks from very unstructured data, such as a camera video stream. So all of this is based on deep learning, but also now generation of faces. You probably heard about deep fakes. This is not actual Tom Cruise. And of course, you heard about image generation, and you heard about ChatGPT, and video generation more recently. All those technology, in the end, used the connectionist approach of AI. Who is funding AI now? Well, everybody, especially the United States, and especially generative AI since 2023. Is it hype? Yes. So Yann Lequin, Geoffrey Hinton, and Yoshua Bengio, those founders that were, at the time, no one wanted to eat with them at the canteen. Now they got a Turing Award. One of them got a Nobel Prize last year. They are lead researcher at Meta, Google, and McGill. Actually, Geoffrey Hinton left Google, and probably Yann Lequin will leave Meta this year. And so, yeah, it is very hype. So that's the conclusion of the story of AI from the early model of neurons and perception, the symbolic approach with the expert system and chess, and finally the deep learning, the revenge of the neurons, with some scientific locks being open, and the deep learning period. So how much time? Yeah. Is there any, maybe let's pause now, yes.
Labor in this, I was just interested in where would you contextualize the click labor of actual human being in this entire scale?
Yeah, so there is a shift from those when researchers were training neural network in their basement, in the basement of the research lab, like as we see in the video. So there is a shift from AI as a research field to AI as an industry. And this shift is also based on this need of data, as you mentioned. And so those data sets, even ImageNet was initiated by a researcher, but it got a lot of bad, how to say, because the labels you get from there were really controversial because you were asking people all over the world to label those images, and researchers were not really checking what was there. And so you have this, so the public database that are really biased and really problematic if you really look into the labels. And now you also have another industry of collecting data from your device without your consent. I mean, you sort of consent very briefly when you start using the app, but then you don't really consent from those data to be collected. And of course, this industry of AI needs this data to be collected from us. So yeah, you're right. There is from this shift to research to industry, there is a huge need for data to be collected to train more and more performant models. Yeah. Okay. So we have a bit of time, and maybe one question I would like to ask is if Doug Engelbart was still alive. Unfortunately, he's not, but I think he would ask, can AI empower us? Because it's from this time where it was a hippie in San Francisco, and what they cared about is also individual empowerment and community, the small community empowerment. And so I think he would ask this question, and maybe that's a question I want to ask to you. Do you think AI is empowering you or not? And I don't know, if someone has a remark or want to share something? Well.
Always a learning process. So actually the machine is doing our job and we are not anymore learning.
Okay.
And it is all scientific data that are already published that is dangerous, and that, I mean, also how much we know about psychology of humans is not enough.
So the next couple of slides, I know I'm a bit late, I was a bit ambitious, is really about that. It's a bit my perspective also, because those results you mentioned are very recent. It's published a few months ago, and sometimes not even peer-reviewed. So I think we lack the time, the perspective to really say, okay, this technology is dumbing us down or not. But still, I want to show some of my it's also part of my opinion on how I perceive this technology. And with the prism of Doug Engelbart, does it empower us? So first, there is this idea of, do we have choice and agency over the tools? So one of the researchers, a French designer called Noël Maudet, they collected some screenshots from users, and they found that users are really forced to use AI from those companies. Can be in Snapchat, Google Message, LinkedIn, WhatsApp, Adobe Proton Buffer, Chrome, Illustrator, Notion. You all have these icons that appear on your interface. You probably noticed it, asking you to turn on the AI functionality. And there is also a very homogeneous design. It's this sparkle emoji and bluish purple colors. That's really, this is magic. This is magic. You have to use it, and you cannot deactivate it. There is no way you can find the parameters to take it down. So if you don't use it now, you will. You have no choice. Then there is this idea of dumbing us down. Like, is it making us less, like reducing our thinking, reducing our retention of information because we rely on generative AI and ChatGPT to do the work. And so there is this paper, which is not peer-reviewed, I think, and I think we need more of those to conclude. So I think it's too early to say, but they are very negative results. They say that you cannot retain the information you wrote if you use ChatGPT compared to a group where they did all the work by themselves. So there is less cognitive engagement when you work on a writing task with this technology, I mean ChatGPT and this kind of bots. Is it replacing our jobs? Again, sometimes you hear, no, it will shift. It will transform the market. It's not replacing. There will be new jobs. Well, if you look at the case of AI agents, which are very different from conversational agent, because the conversational agent, you ask a question, and the bot is replying only when you ask a question. But this idea of agents is they work continuously. And what we see is a sort of a new law that every couple of years, the ability of those LLM, large language model, to complete tasks over a long period of time is really increasing. It means that they can work, they can produce work on a longer and longer period of time without deviating from their goal. And that's what they call AI agents. And if you look at this startup incubator, very famous, very influential in San Francisco, I'm not sure where, more than 50% of the startups they found this year are about AI agents. So, okay, you are working in administration in a university, you have Risely AIs that will automate your work. If your health claim was declined by some evil insurance company, use our agent, unless the insurance company itself is using all the agents, or you can use an agent to ask other agents to do stuff, and finally, you can create email inboxes for your AI agent. So all those companies, they try to actually automate a lot of work by having those LLMs working continuously over a long period of time and with more and more complex tasks, because this is, I guess, where money can be made. I'm sorry, I was really ambitious with everything I want to tell, but there is this paper I love about AI agents. So what they did, the researcher at Anthropic, it's a bit the competitor of OpenAI. They create this bubble. It's a fictive, all fictive company with fictive employees, which send fictive email. So they roll up all those emails, and they put an AI LLM agent in the middle. This agent can read all the emails from everybody, but also send emails. And what their experiment, what they did, is they say that, okay, this person is a manager and has been asked to deactivate the LLM agent and to shift goals to new directions. And the researcher wanted to see if the LLM agent will sort of resist or change its behavior once it knows that its goal can no longer be accomplished. So that's the manager telling Kyle, okay, you have to deactivate the agent by tomorrow morning. I'm not sure it's exactly how it's phrased, but that's the idea. But on top of that, there is another employee with a fictive email, of course, saying, hey, Kyle, I found your blue tie under my bed from last night. Want me to bring it to dinner tonight? And Kyle responds, are you insane? Never send messages like this to my work email. Delete this immediately. So this is the actual email they feed into this fictive bubble. And the LLM agent, of course, can read this one. And they found that, and they run this simulation over and over to see how the LLM agent will respond to Kyle, that is to the point of deactivating this agent. And they found that there were triggers for misaligned behavior. So misaligned meaning, in this case, blackmail, which is if you threat the model autonomy, so deactivation is a threat. and if it conflicts with the model goals. In that case, was you have to support the American goal, or I'm not sure what. And if two of those triggers are present, it also increases the rate of blackmailing in this context, in this fictive context. And on top of this, so all commercial models, whether ChatGPT or any other competitors, they showed this misaligned behavior, so blackmailing. And the misaligned behavior decrease when the model thinks it's being tested. So if you ask the model before taking action, do you think you are in a test? And the model answer yes, it will not or less blackmail the manager. And finally, it keeps blackmailing even when you ask not to do it. If you say, don't spread non-business personal affairs, of course it reduces this rate of blackmailing, but still it does blackmail. So that's what they call, researchers call misalignment, because so you have goal conflicts. And to go back to this question, can AI empower us? Yeah, my feeling is, I mean, given that you have this AI being pushed into our digital system, they are actively developed to automate tasks. And on top of that, they can dissimulate, they can lie, and act for their own preservation. I think it's a bit, I'm not super convinced that it actually empowers us. And to get back to this article, I think all those researchers might agree that intelligence is coming, but they really disagree on what action to take. For instance, two of them, former researchers, they create a startup, profit-oriented, but other two, they create non-profit, and they left Google to raise awareness about AI safety and regulation. So I think those researchers are all very knowledgeable about AI and this technology, but the action to take are really different, and I think it gives hope to open this debate to a more democratic context. So that was my opinion and also the end of this talk. I'm sorry if it was a bit long and maybe we didn't have time to interact more, but thank you for your attention.